The Mitsubishi A6M Zero was obsolete the day it was deployed, yet it ruled the Pacific skies for 2 years. It carried no armor, no self-sealing fuel tanks, and flew with an engine that produced less horsepower than its enemies. 5 American P-40 Warhawks could dive faster, absorb more punishment, and deliver heavier firepower. Yet in the opening months of the Pacific War, a single Zero pilot could engage multiple Allied fighters and emerge victorious. The contradiction defied everything Allied planners believed about air combat. Before we go deeper into how this decision changed the Pacific War forever, make sure to subscribe for more history that actually happened. The answer lay not in what the Zero carried, but in what it deliberately left behind. While American engineers armored their fighters with steel plate and redundant systems, Japanese designers made a different calculation, one that would transform the nature of aerial warfare over the Pacific and force the United States to rewrite its doctrine in blood. The Zero's dominance emerged not from technological superiority alone, but from a design philosophy that accepted sacrifice in service of a single, overwhelming advantage: the ability to turn inside any opponent's defensive circle at speeds where other fighters stalled and fell from the sky. In the winter of 1941, American pilots learned this lesson in the hardest way imaginable. Over the Philippines, Java, and Darwin, P-40 squadrons encountered an enemy that violated every assumption about fighter performance. The Zeros appeared faster than intelligence reports suggested, climbed at angles that seemed physically impossible, and turned with a radius so tight that American pilots found themselves staring down the barrels of 20mm cannon before they understood what had happened. 5 P-40s might scatter a Zero formation with a diving attack, but if any Warhawk pilot accepted the invitation to maneuver, to circle and dogfight as doctrine taught, the engagement ended with an aluminum coffin spiraling into the Pacific or burning on a jungle runway. The strategic landscape of the Pacific in 1937 appeared deceptively stable. American battleships dominated Pearl Harbor. British and Dutch colonial forces controlled Southeast Asia's resources. The Soviet Union maintained armies along Manchuria's border. Yet beneath surface calm, tensions escalated toward inevitable conflict. Japan's invasion of China in July 1937 triggered international condemnation but revealed deeper strategic problems that Japanese naval planners understood with uncomfortable clarity. The empire's expansion depended entirely on imported raw materials: oil from the Netherlands East Indies, rubber from Malaya, iron ore from the Philippines, bauxite from British colonies. Any conflict with Western powers would sever these supply lines unless Japan could secure them through military conquest before American or British forces mobilized effectively. The geography imposed brutal constraints. Japan's home islands lay 2,000 miles north of the Philippines, 2,500 miles from Java, 3,000 miles from Singapore. Land-based aircraft could not reach these targets from Japanese territory. Even medium bombers lacked the range for round-trip missions to crucial objectives. Carrier aviation represented the only means of projecting air power across these oceanic distances. But carriers operated with inherent vulnerability. They moved slowly, required destroyer escorts, and remained exposed to submarine attack. Carrier-based fighters had to reach targets hundreds of miles distant, provide effective combat air patrol over the task force, and possess sufficient performance to dominate enemy defenders. Existing carrier fighters could not meet these demands. The Imperial Japanese Navy issued its specification for a new carrier-based fighter on May 19, 1937. The document bore the designation 12-sha, marking it as a requirement issued in the 12th year of Emperor Hirohito's reign. The parameters seemed contradictory to the point of fantasy. The Navy demanded a fighter capable of 310 miles per hour at 13,000 feet, a range of 1,200 nautical miles with drop tanks, a climb rate that would reach 9,800 feet in 3.5 minutes, an armament consisting of 2 20mm cannon and 2 7.7mm machine guns. The aircraft had to operate from carrier decks, which meant reinforced landing gear, folding wings, and the structural integrity to survive arrested landings. Most critically, it had to possess maneuverability superior to existing fighters, specifically the Nakajima Ki-27 Army fighter, itself considered exceptionally agile. The Navy made these demands at a moment when Japan faced strategic isolation. The empire had invaded China in 1937, triggering international condemnation and American embargoes on scrap metal and aviation fuel. Japanese naval strategists understood that any war with Western powers would unfold across vast oceanic distances where land-based aircraft could not reach. Carrier aviation represented Japan's only means of projecting air power into the Pacific and Indian Oceans. But carriers operated hundreds of miles from their targets, requiring fighters with range that existing designs could not provide. The Zero had to fly escort missions lasting 6 hours while retaining enough fuel and ammunition to engage enemy fighters over the target and return to a moving carrier that might be under attack. Mitsubishi Heavy Industries received the specification in June 1937. Chief designer Jiro Horikoshi assembled a team of 20 engineers who understood immediately that conventional approaches would fail. American and European fighters of 1937 weighed between 5,500 and 6,500 pounds fully loaded. The Navy's speed and climb requirement suggested an engine in the 1,000 horsepower range. But achieving the specified range with that power plant meant reducing weight to unprecedented levels. Horikoshi calculated that the finished fighter could weigh no more than 5,300 pounds combat loaded, nearly a ton lighter than equivalent Western designs. Every component, every rivet, every square inch of aluminum skin had to be optimized for minimum weight while maintaining structural integrity sufficient for carrier operations and the stress of combat maneuvering. Horikoshi's team began with aerodynamic efficiency. The Zero employed a smooth, flush-riveted aluminum skin that reduced parasitic drag. The engine cowling integrated tightly with the fuselage, minimizing the drag penalty from the large radial engine. Retractable landing gear eliminated the exposed wheels that created drag on fixed-gear fighters. The wing used a thick airfoil section, 14% thickness-to-chord ratio, that provided high lift at low speeds while maintaining laminar flow at cruise velocities. Mitsubishi engineers calculated that achieving the specified performance required reducing zero lift drag coefficient to approximately 0.0190, lower than any existing fighter. But aerodynamic refinement alone could not overcome the weight problem. The specified range demanded fuel capacity exceeding 140 gallons for internal tanks, plus provisions for a 75-gallon drop tank. Aviation gasoline weighs roughly 6 pounds per gallon, meaning fuel alone added 840 pounds to the aircraft. The Seiki 12 engine weighed 1,200 pounds dry, plus another 200 pounds for the oil system, engine mounts, and cowling. The two 20mm cannon weighed 26 pounds each, the two 7.7mm machine guns 22 pounds each, plus mounting hardware and ammunition. Landing gear strong enough for carrier operations required substantial structure. The wing spars had to withstand not just flight loads but the 8G impact of arrested landings. Before adding fuselage, tail surfaces, cockpit, or avionics, the Zero's minimum empty weight approached 3,400 pounds using conventional construction. Adding a conventional airframe would push combat weight beyond 6,200 pounds, too heavy to meet performance specifications with the available engine power. The solution emerged from metallurgy rather than aerodynamics. In 1935, Sumitomo Metals Industries had developed an aluminum alloy designated Extra Super Duraluminum. The designation reflected marketing as much as chemistry. The material consisted of aluminum alloyed with zinc, magnesium, and copper in proportions that yielded tensile strength exceeding 85,000 pounds per square inch, roughly 30% stronger than the 24ST aluminum used in American aircraft. Extra Super Duraluminum allowed Horikoshi to reduce skin thickness and lightening existing structural members without compromising strength. Mitsubishi used the alloy for wing spars, fuselage longerons, and load-bearing bulkheads, saving approximately 340 pounds compared to conventional construction. Weight reduction continued through every system. Horikoshi eliminated pilot armor entirely, calculating that the weight penalty, roughly 140 pounds for seatback and headrest armor, reduced performance more than the protection justified. The Zero's fuel system used thin-wall tanks without self-sealing rubber liners, saving another 200 pounds but leaving the aircraft catastrophically vulnerable to incendiary ammunition. The landing gear retracted manually through a chain and pulley system rather than hydraulic actuators, trimming 60 pounds. Even the control surfaces reflected the obsession with lightness. The ailerons, elevators, and rudder operated through direct cable linkage without hydraulic boost, reducing weight while imposing severe physical loads on pilots at high speeds where airflow forces increased exponentially. The engine selection proved equally critical. Mitsubishi designed the airframe around the Nakajima Seiki 12, a 14-cylinder air-cooled radial producing 940 horsepower at takeoff and 950 horsepower at 13,780 feet. The Seiki 12 weighed 1,200 pounds dry, making it one of the lightest engines in its power class. Its two-row radial configuration provided good reliability and simplified maintenance compared to liquid-cooled inline engines. But the Seiki's modest power output meant that the Zero's performance depended entirely on keeping weight minimal. Every pound added reduced climb rate, decreased maximum speed, and degraded maneuverability, the three parameters that would determine survival in combat. Horikoshi's weight reduction campaign extended beyond materials to every system. The cockpit instrumentation used lightweight gauges with aluminum cases rather than steel. The pilot seat employed a tubular aluminum frame with fabric covering instead of heavy armored construction. The control stick and rudder pedals connected directly to flight surfaces through steel cables running over lightweight aluminum pulleys, eliminating hydraulic actuators and their associated plumbing, pumps, and fluid reservoirs. The canopy employed lightweight plexiglass framing that provided excellent visibility but offered no ballistic protection. Even the radio equipment, a standard Type 96 Ku-1 transceiver, was stripped down to minimize weight, though this reduced range and reliability. The landing gear represented perhaps the most ingenious weight-saving measure. Rather than using heavy hydraulic actuators to retract the wheels, Mitsubishi designed a manual system. The pilot operated a hand crank located on the left cockpit wall, turning it 85 times to raise the gear or lower it through a chain and pulley mechanism. The system weighed roughly 60 pounds less than hydraulic alternatives, but imposed significant physical workload on pilots. During combat, pilots often left the gear extended to avoid the distraction of manually cranking while maneuvering against enemies. The fixed gear penalty increased drag, reducing maximum speed by approximately 25 miles per hour and decreasing range by 15%, proved preferable to the vulnerability of focusing on gear operation while under attack. Fuel system design reflected the same ruthless prioritization of weight over protection. American fighters of 1940 to 41 employed self-sealing fuel tanks, rubber bladders surrounded by multiple layers of self-healing materials that swelled when punctured by gunfire, sealing holes within seconds and preventing catastrophic fuel loss. These systems added approximately 200 pounds per aircraft. Horikoshi calculated that this weight penalty reduced performance sufficiently to offset the protection benefit. The Zero used thin-walled aluminum tanks with no self-sealing capability. A single incendiary bullet striking a fuel tank would ignite aviation gasoline, producing a fireball that consumed the aircraft within seconds. Zero pilots understood this vulnerability and teamly, they flew knowing that any hit to the fuel system meant certain death, with no possibility of controlling fire or making an emergency landing. The psychological burden proved immense, but the alternative meant accepting aircraft too heavy and slow to compete with enemy fighters. The first prototype, designated A6M, rolled out of Mitsubishi's Nagoya factory on March 16, 1939. Company test pilot Katsuzo Shima conducted the maiden flight on April 1, flying from Kagamigahara Airfield. The aircraft handled well from the outset, demonstrating light control forces and excellent visibility from the canopy. Initial testing revealed a maximum speed of 304 miles per hour at 9,840 feet and a climb rate of 2,362 feet per minute, both below specification. Mitsubishi replaced the prototype's Mitsubishi Zu Issei 13 engine with the more powerful Nakajima Seiki 12 in the second prototype, designated A6M2. The Seiki installation transformed performance. Maximum speed increased to 316 miles per hour at 14,930 feet. Rate of climb improved to 2,755 feet per minute. Most importantly, the combination of low weight and adequate power produced turn performance that astonished test pilots. The Zero could complete a sustained 360-degree turn at 160 miles per hour indicated airspeed in approximately 16 seconds, yielding a turn radius of roughly 500 feet. At that speed, wing loading, the ratio of aircraft weight to wing area, measured just 22 pounds per square foot, compared to 30 pounds per square foot for the P-40 Warhawk and 34 pounds per square foot for the Navy's own Grumman F-4F Wildcat. Low wing loading produced a stall speed below 60 miles per hour, allowing Zero pilots to slow dramatically during turning engagements while maintaining full control authority. The aircraft's roll rate at 160 miles per hour reached 56 degrees per second, fast enough to reverse turn direction and counter an opponent's maneuver. The combination proved deadly in combat. A Zero pilot could enter a turn, observe his opponent struggling to match the rate, then reverse direction and position for a deflection shot before the enemy completed his turn. But the Zero's phenomenal low-speed handling came with inherent limitations that Horikoshi understood but could not eliminate. The wing's high-lift design used conventional fabric-covered ailerons without metal skinning, a weight-saving measure that introduced dangerous flexibility. As airspeed increased beyond 275 miles per hour indicated, aerodynamic loads deflected the ailerons in the opposite direction intended, a phenomenon called aileron reversal. A pilot attempting a sharp roll to the right at 300 miles per hour would find the aircraft rolling sluggishly left as the fabric control surface ballooned upward under pressure. This made the Zero nearly uncontrollable in high-speed combat maneuvering and rendered it vulnerable to diving attacks where its lighter opponents could accelerate beyond 350 miles per hour, execute rolling maneuvers, and escape before the Zero could respond. Additionally, the Zero lacked hydraulic boost for its control surfaces. At speeds above 300 miles per hour, stick forces increased so dramatically that pilots could barely move the controls. What felt light and responsive at 180 miles per hour became leaden and unmanageable at 320. This characteristic meant that Zero pilots had to fight at speeds where their maneuverability advantage peaked, roughly between 150 and 230 miles per hour. In that envelope, the Zero dominated. Outside it, the aircraft became a liability. The Imperial Japanese Navy accepted the A6M II for service in July 1940, designating it the Type 0 carrier fighter, 0 indicating the year 2600 in the Japanese calendar, corresponding to 1940 in the Western system. The name abbreviated to Zerosen in Japanese parlance and simply Zero among Allied forces. Production began at Mitsubishi's Nagoya plant with Nakojima Hikoki KK adding a second production line at Koizumi. The Navy initially ordered 60 aircraft, expanding orders rapidly as performance reports from operational units confirmed the fighter's extraordinary capabilities. Production Zeros began reaching frontline units in July 1940. The 12th Combined Naval Air Corps received the first operational aircraft, with pilots transitioning from the older A5M Claude fighter. The performance improvement stunned experienced aviators. The A5M, Japan's previous frontline carrier fighter, achieved maximum speed of 270 miles per hour and climbed to 9,800 feet in approximately 5 minutes. The Zero reached 316 miles per hour and climbed to the same altitude in just 3.7 minutes. Turn performance improved even more dramatically. Where the A5M required roughly 20 seconds for a complete 360-degree turn at optimal speed, the Zero completed the same maneuver in 16 seconds. Pilots reported that the Zero felt alive, responding instantly to control inputs and maintaining energy through maneuvers that would have left the A5M wallowing at stall speed. But the Zero's handling characteristics demanded adaptation. The light wing loading and large control surfaces produced extreme sensitivity at low speeds. Inexperienced pilots over-controlled, inducing oscillations that required opposite corrections. The manual landing gear forced pilots to divide attention between flying and cranking during critical phases of flight. The narrow-track landing gear, wheels positioned close together to fit within the streamlined fuselage, made ground handling tricky, with any crosswind threatening to ground. Loop the aircraft. Carrier landings proved especially demanding. The Zero's low stall speed and light weight made it easy to land aboard carriers in calm conditions, but the aircraft's light structure meant that hard landings risked structural damage. Pilots learned to touch down gently, accepting the risk of wave-off if they could not achieve proper approach speed and attitude. The Zero entered combat on August 19, 1940, when 13 fighters from the 12th Combined Naval Air Corps escorted bombers attacking Chongqing, deep in China's interior. The mission covered 1,130 miles round-trip, far beyond the range of any existing fighter. Chinese defenders expected unescorted bombers and launched 30 Polikarpov IE-15 and IE-16 fighters to intercept. The Zero pilots engaged immediately, demonstrating the aircraft's superiority in turning combat. Within minutes, Zero pilots claimed 27 Chinese fighters destroyed without loss. Chinese pilots reported that the new Japanese fighters could turn inside their tightest maneuvers and maintain energy throughout extended engagements. Subsequent combat over China through late 1940 and 1941 reinforced the Zero's dominance. Japanese pilots developed tactics exploiting the aircraft's strengths while avoiding its weaknesses. The standard engagement began with a high-speed approach using altitude advantage and surprise. Zero pilots would dive on enemy formations, make a single firing pass, then convert excess speed to altitude through a zoom climb. If the enemy scattered, pursuit followed using the Zero's superior sustained turn rate. If opponents tried to dogfight, Zero pilots would slow to 180 to 200 miles per hour, where their turn advantage reached its peak, and circle inside the enemy's defensive turns until positioning for a killing shot. The 20mm cannon carried just 60 rounds per gun, but each shell packed enough explosive to destroy an aircraft with a single hit. Pilots learned to close to 300 feet before firing, ensuring accuracy and maximum damage. Chinese pilots who survived encounters with Zero's reported aircraft performance that seemed impossible. They described Japanese fighters appearing at altitudes previously considered safe, turning inside Chinese defensive maneuvers, and maintaining sustained combat for hours far from any known Japanese airfield. Intelligence analysts cross-referenced these reports with known Japanese industrial capabilities and concluded that the descriptions represented multiple aircraft types conflated through combat stress and confusion. The reports described carrier-based fighters exceeding 320 miles per hour while carrying heavy cannon armament, performance that American carriers' fighters could not approach. The Navy's own Grumman F-4F Wildcat, considered a capable design, achieved 328 miles per hour maximum but sacrificed armament and range to reach that speed. The notion that Japan had developed a carrier fighter superior to America's best seemed implausible given the empire's perceived industrial backwardness. This analytical failure reflected systematic underestimation of Japanese engineering capability rooted in racial prejudice and intelligence gaps. American military assessments through the 1930s consistently portrayed Japan as technologically inferior, copying Western designs but lacking innovation capacity. Intelligence estimates suggested Japanese engines produce 700 to 800 horsepower maximum, aircraft construction employed inferior materials, and Japanese pilots possessed inadequate training. These assumptions proved catastrophically wrong. Japanese aeronautical engineering had advanced significantly through the 1930s, developing indigenous designs that matched or exceeded Western equivalents. The Seiki-12 engine represented sophisticated engineering, incorporating advanced metallurgy and precise manufacturing. Japanese pilots trained extensively, with carrier pilots accumulating over 300 hours before joining operational squadrons, more than many American naval aviators of the period. American intelligence officers received reports of the Zero's performance throughout 1941 but dismissed most accounts as exaggeration. The description, a carrier-based fighter matching or exceeding the performance of land-based interceptors, seemed physically impossible given known Japanese industrial capabilities. Intelligence estimates suggested that Japanese engines produced roughly 750 horsepower, insufficient to power a fighter achieving 330 miles per hour while carrying the reported armament. The logical conclusion held that pilots were encountering multiple aircraft types and conflating their capabilities into a single mythical fighter. When Claire Chennault, commander of the American volunteer group, Flying Tigers, in China, reported Zero specifications and combat tactics to Washington in early 1941, his intelligence summaries received polite acknowledgement but generated no doctrinal response. This skepticism evaporated on December 7, 1941. The attack on Pearl Harbor employed 126 Zeros from 6 aircraft carriers operating in 2 waves. The fighters provided escort for bombers and conducted strafing attacks on airfields, destroying American aircraft on the ground while engaging the handful of defenders that managed to take off. Zero pilots claimed 10 aerial victories during the Pearl Harbor raid while losing just 9 aircraft to all causes, including anti-aircraft fire. But Pearl Harbor represented a strike against unprepared defenses. The real test came in the following days and weeks, when Zero fighters encountered American and Allied pilots in the Philippines, Malaya, and the Netherlands East Indies. On December 8, 1941, Japanese naval aircraft from Formosa struck American airfields in the Philippines. The raid destroyed most of General Douglas MacArthur's Far East Air Force on the ground, but surviving P-40s from the 3rd Pursuit Squadron managed to intercept subsequent raids. The P-40 pilots found themselves facing an opponent unlike anything their training had prepared them for. The Zeros could climb faster, turn tighter, and sustain combat at altitudes where the P-40's Allison VR-1710 engine struggled. First Lieutenant Boyd Wagner engaged multiple Zeros over Bataan Peninsula and survived by refusing to turn with his opponents, instead using the P-40's superior dive speed and rolling rate to escape after each firing pass. The tactical pattern repeated across the Pacific. At Darwin, Australia, on February 19, 1942, Zero fighters from FA aircraft carriers escorted a massive bombing raid that devastated the harbour and airfields. Australian and American P-40s attempted to intercept but suffered devastating losses. 8 P-40s were shot down in aerial combat against Zeros while the Japanese lost just 2 fighters. At Java, Royal Air Force and Dutch pilots flying Hurricanes and Brewster Buffaloes encountered the same problem. Any attempt to maneuver with Zeros ended with the Allied fighter burning on the jungle floor or splashing into the ocean. The tactical pattern that emerged across the Pacific in December 1941 and January 1942 revealed systematic Allied disadvantages beyond individual aircraft performance. Japanese forces operated with comprehensive intelligence regarding Allied dispositions, aircraft types, and defensive capabilities. The Pearl Harbor strike demonstrated precise knowledge of American ship locations, aircraft numbers, and defensive preparations. Subsequent attacks on the Philippines, Malaya, and the Netherlands East Indies showed similar intelligence preparation. Japanese forces struck with overwhelming numerical superiority at carefully chosen times when weather, light conditions, and tactical circumstances favored the attackers. Allied responses suffered from intelligence failure, inadequate preparation, and doctrinal confusion. American and British commanders anticipated Japanese attacks but misjudged the timing, direction, and scale. The destruction of B-17 bombers on Philippine airfields hours after Pearl Harbor revealed catastrophic command failures. Aircraft sat in neat rows without dispersal or protection despite clear warning that war had begun. Fighter squadrons scrambled piecemeal to intercept raids, arriving at combat altitude after Japanese formations had already dropped bombs and were departing. Radar coverage remained sparse and unreliable, limiting early warning. Ground control interception techniques developed in Europe saw limited implementation in the Pacific. When Allied fighters did engage, they discovered opponents flying aircraft that violated every assumption about Japanese capabilities. Intelligence briefings described Japanese fighters as slow, poorly armed, and fragile. The reality proved opposite. Zero fighters arrived at American formations already at altitude, pressed attacks aggressively, and demonstrated maneuverability that rendered standard defensive tactics useless. Allied pilots trained in Europe emphasized formation integrity and mutual support. Against Zeros, formations disintegrated within seconds as individual aircraft turned to engage opponents that simply turned inside their defensive circles. The psychological impact proved devastating. Pilots accustomed to confidence in their aircraft and training found themselves helpless, watching comrades die while unable to position for effective counterattack. The Curtiss P-40 Warhawk represented America's frontline fighter in December 1941. Derived from the earlier P-36 Hawk by replacing the radial engine with an Allison VR-1710 liquid-cooled inline engine, the P-40 first flew in October 1938. The design emphasized reliability, durability, and straightforward maintenance rather than cutting-edge performance. The P-40E variant, most common in the Pacific during early 1942, weighed 8,720 pounds fully loaded, roughly 3,400 pounds heavier than the Zero. This weight included 197 pounds of armor protecting the pilot and critical systems, self-sealing fuel tanks with rubber liners that could absorb small-caliber hits without leaking, and rugged construction using thick aluminum skin and substantial internal structure. The Allison V1710-39 engine produced 1,150 horsepower at takeoff, giving the P-40E superior power compared to the Zero's Saki 12. But the power-to-weight ratio told a different story. The Zero's 940 horsepower pushed 5,300 pounds, roughly 5.6 pounds per horsepower. The P-40's 1,150 horsepower moved 8,720 pounds, approximately 7.6 pounds per horsepower. This disparity translated directly into performance. The P-40E achieved a maximum speed of 360 miles per hour at 15,000 feet and climbed at 2,100 feet per minute, competitive with the Zero's 316 miles per hour and 2,755 feet per minute, but clearly inferior. The real gap emerged in turning performance. The P-40's wing loading of 30 pounds per square foot and heavier mass produced a turn radius roughly double the Zero's at equivalent speeds. A P-40 attempting to turn with a Zero at 180 miles per hour would complete the circle in approximately 26 seconds, giving the Zero pilot 10 full seconds to position, track, and fire. The P-40's strengths lay in areas irrelevant to turning dogfights. The Allison engine delivered full power to 12,000 feet before manifold pressure dropped, giving the Warhawk superior performance at low altitudes where most Pacific combat occurred. The aircraft could dive at speeds exceeding 450 miles per hour without structural failure, compared to the Zero's maximum demonstrated dive speed of approximately 410 miles per hour. The P-40's 6.50 caliber machine guns delivered 200 rounds per second of fire, less destructive per hit than the Zero's 20mm cannon but sufficient to shred an unarmored opponent. And the Warhawk could absorb battle damage that would destroy a Zero. The armor plate stopped 7.7mm rounds completely and deflected 20mm fragments. The self-sealing tanks contained fuel leaks within seconds of puncture. Pilots regularly returned with holes torn through wings and fuselage, damage that would have sent a Zero spinning into the sea in flames. But in December 1941, American fighter doctrine emphasized classic dogfighting, circling combat where maneuverability determined the victor. Training taught pilots to engage opponents in turning duels, using superior position and patience to force the enemy into increasingly desperate maneuvers until presenting a shot. The tactics assumed rough parity in performance. Against the Zero, these methods proved suicidal. American pilots entered turning contests confident in their training and found themselves watching in horror as the Zero simply turned inside their defensive circles, centered the gunsight pipper on their canopy, and fired. The P-40's design philosophy reflected American aviation doctrine of the late 1930s, which emphasized firepower, durability, and ease of maintenance over extreme performance. Curtiss engineers designed the Warhawk for mass production, using straightforward construction techniques that permitted rapid manufacturing by semi-skilled workers. The aircraft employed conventional stressed skin aluminum construction with heavy internal structure and redundant load paths. If one structural member failed in combat, adjacent members could carry loads until the pilot returned to base. This approach contrasted sharply with the Zero's weight-optimized design where single structural failures could prove catastrophic. The Allison VR-1710 engine represented America's only indigenous liquid-cooled VR-12 engine in production during 1941. The engine delivered reliable performance but lacked the two-stage supercharging necessary for high-altitude operations. The single-stage, single-speed supercharger maintained manifold pressure to approximately 12,000 feet, providing excellent low-altitude performance where most Pacific combat occurred. Above 15,000 feet, power dropped significantly as atmospheric pressure decreased and the supercharger could not compensate. This altitude limitation proved less significant in the Pacific than in Europe, where bombers routinely operated above 20,000 feet, but still restricted tactical options against Zeros that could climb rapidly to altitude and dive on P-40 formations from above. P-40 armament evolved through successive variants. The P-40B and P-40C employed 2.50 caliber machine guns in the nose and 4.30 caliber machine guns in the wings. The P-40E upgraded to 6.50 caliber machine guns, all mounted in the wings. The .50 caliber Browning M2 machine gun fired 750 to 850 rounds per minute, delivering projectiles weighing 1.5 ounces at muzzle velocity of 2,840 feet per second. Standard ammunition mixed armor-piercing incendiary, tracer, and ball rounds. Against unarmored targets like the Zero, the .50 caliber proved devastatingly effective. A 2-second burst from 6 guns delivered approximately 180 rounds, and just 3 or 4 hits could sever flight control cables, destroy the engine, or ignite fuel tanks. The challenge lay in positioning to deliver that burst against an opponent that turned inside every defensive maneuver. The P-40's armor protection reflected hard-won lessons from European combat. A steel plate measuring 8 mm thickness protected the pilot's back and head. Bulletproof glass 1.5 inches thick shielded the pilot from frontal attack. The engine compartment included armor protecting the oil cooler and glycol radiator, both vulnerable to small arms fire and essential for engine operation. This armor weighed 197 pounds but proved its worth in combat. P-40 pilots routinely returned with bullet holes in wings, fuselage, and tail, damage that would have destroyed a Zero but left the Warhawk flyable. The self-sealing fuel tanks contained hits without fuel loss, allowing pilots to disengage and return to base even after absorbing significant battle damage. The solution emerged from observation and bitter experience rather than doctrinal innovation. Claire Chennault's American Volunteer Group, operating in China and Burma from December 1941 through July 1942, pioneered tactics that exploited the P-40's strengths while avoiding its weaknesses. Chennault had observed Zero combat tactics throughout 1941 and understood the aircraft's vulnerabilities. He instructed his pilots to avoid turning combat entirely, instead employing boom and zoom tactics, diving attacks from superior altitude followed by immediate separation using the P-40's superior dive speed and structural strength. The engagement began with altitude advantage, typically 3,000 to 5,000 feet above the enemy formation. Flying Tigers pilots would spot Zeros below, then push into a high-speed dive reaching 350 to 400 miles per hour. At this speed, the P-40 possessed superior roll rate and controllability while the Zero wallowed with unresponsive controls. The diving pilot would roll onto the target's tail, fire a 2-second burst at close range, then continue the dive past the target and pull up into a zoom climb, converting speed to altitude. If the Zero pilot attempted to follow the diving P-40, he could not match the acceleration and would watch his target escape. If he tried to climb after the zooming Warhawk, the P-40's superior energy would carry it back to altitude before the Zero could close. The critical discipline lay in never accepting combat on the Zero's terms. If a P-40 pilot spotted Zeros at his altitude or above, doctrine demanded immediate disengagement, diving away and using speed to separate, then returning only with altitude advantage restored. If caught low and slow with Zeros above, the only survival strategy involved diving toward terrain or the coast, using ground effect and maximum speed to escape while the Zero's inferior dive performance prevented pursuit. Under no circumstances could a P-40 pilot allow the engagement to devolve into turning combat. That fight had only one outcome. The Flying Tigers applied these tactics with devastating effect. From December 1941 through July 1942, Chennault's 3 squadrons claimed approximately 297 Japanese aircraft destroyed against losses of 14 pilots in aerial combat. The actual numbers remain disputed. Japanese records do not support such extreme kill ratios, and many claimed victories represented damaged aircraft that returned to base. But even conservative analysis confirms that properly employed P-40s could engage Zeros successfully by refusing to fight in the maneuvering envelope where the Zero's advantages became overwhelming. The pattern of early Pacific combat revealed a fundamental truth about fighter design: optimization for specific performance parameters creates simultaneous strengths and weaknesses. The Zero's extreme weight reduction produced unmatched maneuverability at low speeds but created vulnerability to high-speed attacks and any weapon hits. The P-40's heavier construction sacrificed turning performance but provided durability and diving capability. Neither design was inherently superior. Tactical employment determined outcomes. A Zero pilot who accepted a diving fight or attempted to pursue a P-40 in a high-speed dive would die. A P-40 pilot who accepted a turning fight or tried to outclimb a Zero would burn. But in the opening months of 1942, this lesson cost American squadrons dearly. Over the Philippines, P-40 units lost entire flights attempting to dogfight with Zeros. The 17th Pursuit Squadron began the war with 18 P-40s and by December 24, 1941, could muster only 3 flyable aircraft, with most losses coming in air combat. At Java in February and March 1942, P-40 squadrons engaged Japanese carrier strikes and suffered catastrophic attrition. The 17th Provisional Pursuit Squadron lost 9 of its 15 P-40s in a single week of combat, with most pilots reporting the same experience. They turned to engage Zeros and found themselves immediately at a fatal disadvantage. The crisis deepened as the Japanese offensive swept south through the Philippines, Malaya, and the Netherlands East Indies. Every engagement confirmed the Zero's dominance in turning combat. Pilots who survived learned through adaptation or died confirming what their training had taught. Squadron commanders began issuing tactical guidance: don't dogfight with Zeros, maintain speed, use diving attacks only, but institutional doctrine changed slowly while Japanese forces advanced quickly. The Flying Tigers applied these tactics with devastating effect, but their success depended on circumstances unique to the China-Burma-India theater. Chennault squadrons operated from secure bases with adequate warning time to climb to altitude before Japanese formations arrived. The average employed ground observers throughout southern China who radioed aircraft sightings hours before raids reached Allied airfields. This warning allowed P-40 pilots to take off, climb to 20,000 feet, and position themselves above incoming raids. Japanese formations typically approached at 12,000 to 15,000 feet, leaving the Flying Tigers with 5,000 feet altitude advantage, sufficient for boom and zoom attacks. Additionally, Japanese bomber formations over China often operated without Zero escort due to range limitations, allowing P-40s to attack bombers without engaging fighters. The situation in the Philippines, Java, and Darwin differed fundamentally. Zero fighters escorted raids throughout, maintained altitude advantage through superior climb rate, and initiated combat before defending fighters reached favorable positions. P-40 squadrons scrambled from tactical warning provided by coastwatchers or radar, reaching combat altitude after Japanese formations had already begun attack runs. Zero pilots held the high ground and dived on climbing P-40s, forcing engagement in vertical maneuvering where the Zero's superior power-to-weight ratio and climb rate dominated. P-40 pilots attempting to climb away found Zeros following easily, closing range, and firing from positions American pilots could not counter. Doctrine struggled to adapt under combat pressure. Squadron commanders understood that turning with Zeros meant death, but articulating effective alternatives required analysis that combat tempo did not permit. Daily missions left pilots exhausted, with insufficient time for after-action reviews or tactical development. Aircraft losses mounted faster than replacements arrived, forcing squadrons to operate under strength with inexperienced pilots filling gaps left by combat casualties. Training emphasized formation flying and mutual support, but these tactics proved ineffective against opponents that simply turned inside formations and attacked individual aircraft before wingmen could respond. The doctrinal evolution that saved American fighters in 1943 began forming in early 1942 but required months of analysis, testing, and training to implement effectively. The captured Akatan Zero changed everything. On June 4, 1942, during the Battle of the Aleutians, Flight Petty Officer Tadayoshi Koga led a strafing attack on American positions at Dutch Harbor. Ground fire struck his Zero, severing the oil return line. Koga attempted an emergency landing on Akatan Island, 25 miles east of Dutch Harbor. The island appeared to offer a flat grassy field suitable for a wheels-down landing. But the grass concealed soft tundra. When Koga touched down, the wheels dug into the ground and the Zero flipped inverted, crushing the canopy and killing the pilot instantly. The aircraft came to rest upside down, largely intact, in terrain too remote for Japanese forces to recover it. American forces discovered the wrecked Zero on July 10, 1942. Naval intelligence officers recognized immediately that the crash site's isolation and the aircraft's intact condition represented an intelligence windfall. A recovery team disassembled the Zero and transported it to Naval Air Station North Island in San Diego, California. Mechanics spent weeks rebuilding the aircraft, fabricating replacement parts where necessary and restoring the Seki-12 engine to operation. On September 20, 1942, Lieutenant Commander Eddie Sanders of the Navy's Air Test Center at Naval Air Station Pachysant River climbed into the cockpit for the first test flight. The evaluation that followed lasted 3 months and involved pilots from the Navy, Army Air Forces, and Royal Air Force. Each pilot flew the Zero through standard test protocols, speed runs at various altitudes, rate of climb measurements, turning performance at different speeds and configurations, aerobatic maneuvers, and comparative tests against American fighters. The results confirmed everything combat reports had suggested and revealed weaknesses that tactical employment could exploit. The test pilots documented the Zero's extraordinary low-speed handling. Below 200 miles per hour indicated airspeed, the aircraft turned inside every American fighter. The P-40, F for F Wildcat, P-38 Lightning, and even the newer F for U Corsair could not match the Zero's sustained turn rate at these speeds. But above 275 miles per hour, the Zero transformed from a graceful dancer into an uncontrollable brick. The fabric-covered ailerons ballooned under aerodynamic loading, producing aileron reversal that made roll control nearly impossible. Stick forces increased exponentially, requiring both hands and maximum strength to deflect controls. The rudder pedals became immovable at speeds above 320 miles per hour, eliminating the pilot's ability to coordinate turns or correct for adverse yaw. Most critically, the tests revealed that the Zero could not follow a P-40 or F for F through a high-speed rolling dive. At 350 miles per hour indicated airspeed, the American fighters possessed full control authority and could perform snap rolls, split-S reversals, and defensive brakes. The Zero at the same speed wallowed through control inputs delayed by seconds, rendering the pilot unable to track a maneuvering target or evade counterattack. The tests confirmed that boom and zoom tactics represented not just an effective strategy but the only viable approach, engaging the Zero in high-speed regimes where it could not respond. The intelligence derived from the Akatan Zero disseminated throughout Pacific commands by December 1942. Tactical bulletins outlined specific engagement protocols. Maintain altitude advantage. Attack in high-speed dives exceeding 300 miles per hour. Fire a single burst, then immediately extend away in a continued dive. Use zoom climbs to regain altitude. Never slow down. Never turn with the Zero. Never attempt to outclimb a Zero from equal altitude. Fighter squadrons received detailed briefings including gun camera footage from the test flights showing the Zero's behavior at various speeds. The tactical evolution occurred alongside new aircraft introductions. The F-6F Hellcat entered service in January 1943, designed specifically to counter the Zero. The Hellcat sacrificed maneuverability for speed, climb rate, firepower, and durability. Its 2,000 horsepower Pratt & Whitney R2800 engine pushed the aircraft to 380 miles per hour, fast enough to dictate engagement terms, diving on Zeros and extending away before the enemy could respond. The P-38 Lightning provided twin-engine reliability and heavy firepower, while the F for U Corsair combined speed, range, and armament. All three aircraft fought using the same doctrine: avoid turning combat, use speed and altitude, employ hit-and-run tactics. But the shift in tactical approach predated new aircraft. By mid-1943, P-40 squadrons in the Pacific routinely engaged Zeros using boom and zoom tactics with acceptable loss rates. The aircraft remained inferior in a dogfight, but properly employed Warhawks could compete successfully. The change represented doctrinal adaptation rather than technological improvement. American fighter pilots stopped trying to turn with Zeros and started exploiting the weaknesses that extreme weight reduction created. The Zero's dominance faded through 1943 and collapsed in 1944. New American fighters with superior power, speed, and firepower entered service throughout the Pacific. Equally important, American pilot training incorporated lessons from the Akatan Zero and combat experience. Squadron ready rooms displayed charts comparing Zero and American fighter turn radii at various speeds. Training emphasized maintaining energy, refusing slow-speed combat, and using altitude to control engagement geometry. By 1944, rookie pilots fresh from training command understood how to fight Zeros, while in 1941 veteran instructors did not. Japan attempted to improve the Zero through successive variants. The A6M III Model 32 introduced a more powerful Seiki 21 engine with two-stage supercharger, producing 1,130 horsepower. But the Navy demanded increased armament and some pilot protection, adding weight that negated the power increase. The A6M V Model 52 addressed some high-speed handling problems by replacing fabric-covered ailerons with aluminum skin versions and reinforcing the control system. Maximum dive speed increased to approximately 460 miles per hour, and roll rate at 300 miles per hour improved markedly. But these changes came too late. By late 1943, the A6M V faced Hellcats and Corsairs that simply flew around the Zero's maneuvering advantages, engaging in high-speed combat where the American fighter's superior power and durability dominated. The Zero remained in production through the war's end in August 1945, with nearly 10,940 aircraft completed across all variants. Late-war models served primarily as kamikaze aircraft, laden with bombs for one-way suicide attacks on American ships. The fighter that had terrorized Allied forces in 1941 to 1942 became expendable by 1945, its pilots barely trained and its performance hopelessly outclassed by American aircraft that emerged from production lines at rates Japanese industry could not match. The human cost of the Zero's early dominance remains difficult to quantify precisely. American and Allied losses in the Pacific during 1941 to 1942 resulted from multiple causes: Japanese bombing, strafing attacks on parked aircraft, and combat against various Japanese aircraft types. But combat reports consistently identify Zero fighters as the primary threat in aerial engagements. In the Philippines, the Far East Air Force began the war with approximately 270 aircraft and by January 1942 retained fewer than 30 flyable machines, with most losses attributed to combat with Zero fighters. At Java, Allied air forces lost over 100 aircraft in the campaign's final weeks, with Japanese records showing Zero pilots claiming the majority of victories. The tactical lessons proved applicable far beyond the Pacific. In Europe, American and British fighters learned to exploit diving attacks against more maneuverable German fighters when conditions allowed. The fundamental principle, fight in performance regimes where you possess advantages, not where the enemy excels, became doctrine across theaters. The P-47 Thunderbolt, massively heavy at over 14,000 pounds loaded, survived by using speed and diving attacks rather than attempting to turn with lighter opponents. The tactics American pilots developed fighting Zeros informed combat approaches for the remainder of the war. The introduction of superior American fighters in 1943 forced Zero pilots into increasingly desperate situations. The F-6F Hellcat entered combat in August 1943, immediately establishing dominance through sheer performance advantage. The Hellcat's Pratt & Whitney R2800 double Wasp engine produced 2,000 horsepower, more than double the Zero's Seiki 12 output. This power translated into maximum speed of 380 miles per hour, rate of climb exceeding 3,000 feet per minute, and the ability to maintain high speed through combat maneuvers. Hellcat pilots could dive on Zero formations, fire, and climb away before Japanese pilots could respond. If Zero's attempted pursuit, the Hellcat simply accelerated, pulling away while the Zero's engine screamed at maximum power without closing the gap. The F-4U Corsair provided even more dramatic performance. The distinctive inverted gull-wing fighter achieved 417 miles per hour maximum speed with its 2,000 horsepower Pratt & Whitney RA2800, making it the fastest piston fighter of 1943. The Corsair's speed advantage proved so overwhelming that Zero pilots often could not even maneuver into firing position before the American fighter extended beyond gun range. Corsair pilots developed tactics of high-speed slashing attacks, diving through Zero formations at speeds exceeding 400 miles per hour, firing brief bursts, and continuing past without attempting to maneuver. Zero pilots could turn to pursue but found their targets vanishing into the distance before completing the turn. Perhaps most significantly, the P-38 Lightning provided twin-engine reliability and concentrated firepower in a high-speed platform. The Lightning's 4.50 caliber machine guns and single 20mm cannon clustered in the nose, eliminating wing-mounted gun convergence issues and allowing pilots to fire with devastating effect at longer ranges. The twin Allison VR1710 engines produced combined 2,600 horsepower, pushing the P-38 to 414 miles per hour and climb rates exceeding 2,800 feet per minute. The twin-boom design provided redundancy. If one engine sustained battle damage, the pilot could return to base on the remaining engine. Zero pilots found P-38s nearly invulnerable to their standard tactics. The Lightning could outrun, outclimb, and outdive the Zero while delivering firepower that shredded the Japanese fighter's unarmored structure. Japanese attempts to improve the Zero through successive modifications addressed symptoms without solving fundamental problems. The A6M Model 52 introduced metal-skinned ailerons replacing fabric-covered versions, improving roll rate at high speeds and increasing maximum dive speed from 410 to approximately 460 miles per hour. The Model 52 also featured strengthened wing structure allowing steeper dives, and exhaust thrust augmentation that increased maximum speed by roughly 10 miles per hour. These improvements helped, but could not overcome the basic performance gap. An A6M diving at its maximum 460 miles per hour could not catch a Hellcat accelerating to 380 in level flight, then diving at speeds exceeding 450. The Zero remained trapped in a performance envelope optimized for 1940 combat against opponents still flying in 1945. The Navy attempted more radical improvements with variants like the A6M8, which employed a 1,560 horsepower Mitsubishi Kinsei 62 engine replacing the Seiki. The Kinsei installation increased maximum speed to 356 miles per hour and improved climb rate, but the engine's greater weight and fuel consumption negated the Zero signature range advantage. Only 2 A6M8 prototypes were completed before the war ended. The fundamental problem proved insoluble. The Zero's light structure and minimal fuel capacity could not accommodate more powerful engines without redesign so comprehensive that creating an entirely new aircraft made more sense. But Japan lacked resources for new fighter development while maintaining production of existing types. The Zero's design reflected Japan's strategic circumstances with brutal clarity. The empire lacked the industrial capacity to match American production. Japanese aviation fuel refineries could not produce sufficient high-octane gasoline for engines exceeding 1,200 horsepower. Aluminum production remained constrained by limited bauxite imports. Japanese designers responded by creating an aircraft that maximized performance from limited resources through extreme weight reduction and acceptance of vulnerabilities that American designers would never tolerate. The result dominated for 2 years until opponents learned to avoid fighting on Japanese terms and American industry fielded aircraft that simply overpowered the Zero through brute force. In retrospect, the Zero represented both triumph and trap. Horikoshi's design brilliance created an aircraft that achieved seemingly impossible performance from modest power plants and manufacturing resources. For Japan, the Zero provided qualitative superiority that partially offset quantitative inferiority in the war's early months. But the design's fundamental compromises, no armor, no self-sealing tanks, marginal high-speed handling, became increasingly fatal as American tactics evolved and new fighters arrived. The Japanese Navy, committed to the Zero platform, producing variants through 1945 despite recognition that the basic design could not evolve to match newer American aircraft. Developing a successor would have required resources Japan did not possess and time the Pacific War did not permit. The production numbers tell the story of industrial disparity. Mitsubishi and Nakajima produced 10,939 Zeros of all variants between 1940 and 1945, roughly 2,200 aircraft per year at peak production. American factories produced 12,275 Hellcats between 1942 and 1945, 12,571 Corsairs, 10,037 Lightnings, plus thousands of P-47 Thunderbolts, P-51 Mustangs, and other types. American industry outproduced Japanese aircraft manufacturing by ratios exceeding 10-to-1 in fighters alone. This disparity meant that even if the Zero had matched American fighters in performance, numerical superiority would have ensured American victory. Japanese pilots by 1944 often faced battles where 10 or 15 American fighters attacked 2 or 3 Zeros. Individual pilot skill and aircraft maneuverability became irrelevant when overwhelmed by such numbers. Pilot quality suffered even more dramatically than aircraft production. Japan began the war with approximately 3,500 trained naval aviators, many with combat experience from China. These pilots possessed exceptional skill, averaging over 500 flight hours before joining operational squadrons. But Japan's training infrastructure could not replace combat losses at sustainable rates. The Navy graduated roughly 5,400 pilots during the war's first 3 years, while combat, operational accidents, and disease killed approximately 8,900. By late 1944, Zero pilots entered combat with as few as 100 hours total flight time, minimal gunnery training, and essentially no combat instruction. These barely-trained pilots faced American aviators who had completed 200 to 300 hours of training including extensive gunnery, formation flying, and combat tactics instruction. The Battle of the Philippine Sea in June 1944 demonstrated the consequences. Japanese carriers launched approximately 430 aircraft against American Task Force 58. American fighters, primarily Hellcats, intercepted the raid and destroyed roughly 380 Japanese aircraft, approximately 88% of the attacking force. American losses totaled 29 aircraft, yielding a kill ratio exceeding 13-to-1. The battle became known as the Great Marianas Turkey Shoot among American pilots, referencing the ease with which they shot down Japanese aircraft. Zero pilots found themselves unable to penetrate American fighter screens, watching helplessly as Hellcats dove on their formations, picked off aircraft methodically, then climbed away untouched. The few Zeros that reached the American carriers faced devastating anti-aircraft fire from ships equipped with proximity-fused shells and radar-directed fire control that brought down aircraft at ranges where Japanese pilots could not effectively aim their weapons. The lesson remains relevant. Optimization creates specialization, and specialization creates vulnerability. The Zero optimized for low-speed maneuverability at the cost of every other parameter. When opponents adapted to exploit the weaknesses that optimization created, the Zero's advantages became irrelevant. American fighters like the P-40, dismissed as mediocre in 1941, proved adequate when employed correctly. Superior aircraft like the Hellcat and Corsair dominated because they refused to fight where the Zero excelled, instead forcing combat into regimes where American advantages in power, speed, and durability determined outcomes. The human stories behind these statistics reveal dimensions that operational analysis cannot capture. Zero pilots who dominated Pacific skies in 1941 to 1942 found themselves by 1944 to 1945 flying obsolete aircraft against overwhelming opposition with minimal support and no realistic hope of survival. Flight Petty Officer Saburo Sokai, one of Japan's highest-scoring aces with 64 confirmed victories, described the evolution. In 1942, he expected to survive combat through skill and aircraft superiority. By 1944, survival meant luck rather than skill. Flying missions where aircraft outnumbered 5-to-1 made victory impossible regardless of pilot capability. American pilots experienced parallel transformation. Lieutenant Edward Aher shot down 5 Japanese bombers over a ball in February 1942 flying an F-4F Wildcat, an aircraft markedly inferior to the Zero in most performance parameters. Aher survived by refusing to dogfight, using diving attacks and superior gunnery. By 1944, American fighter pilots enjoyed such performance and numerical advantages that combat resembled execution rather than warfare. Lieutenant David McCampbell, who became the Navy's highest-scoring ace with 34 victories, described engagements where American fighters simply positioned behind Japanese formations and fired methodically until all targets fell. The Zero pilots could turn aggressively, but Hellcats held positions outside the turning radius and waited for Japanese aircraft to stall, then moved in for killing shots. The psychological dimension remains largely unexplored in technical histories but proved decisive. Zero pilots in 1941 flew with confidence bordering on invincibility, understanding their aircraft outperformed all opponents. This confidence enabled aggressive tactics, diving into numerically superior formations, accepting combat against unfavorable odds, pressing attacks despite battle damage. By 1944, that confidence had evaporated. Zero pilots understood they flew obsolete aircraft against superior opponents. Combat reports describe Japanese pilots breaking off attacks when they spotted American fighters, refusing engagement unless tactical circumstances provided some advantage. This defensive mindset proved fatal in warfare where initiative and aggression often determined outcomes. American pilots experienced opposite evolution. The P-40 pilots who engaged Zeros in December 1941 flew uncertain of their aircraft, their tactics, or their chances. Combat reports reveal hesitation, confusion, and desperation as pilots discovered their training inadequate for the reality they faced. By 1944, American fighter pilots flew with absolute confidence in their aircraft, their tactics, and their inevitable victory. This confidence enabled aggressive tactics, willingness to engage superior numbers, and persistence through tactical setbacks. The psychological transformation proved as decisive as the hardware improvements. The 5 P-40s that couldn't outmaneuver a single Zero represented not a failure of engineering but a failure of doctrine. American designers built fighters optimized for different combat, heavily armed, durable, capable of absorbing damage and maintaining formation integrity. American doctrine taught circling combat where pilots used maneuver to position for firing solutions. The Zero exploited both assumptions by creating a fighter so light and so maneuverable that it rendered conventional tactics suicidal. The P-40 pilots died learning what their commanders did not teach, that victory comes not from fighting harder within your enemy's chosen arena, but from refusing that arena entirely and forcing combat into domains where your strengths matter and his advantages wither. By 1943, the lesson had taken root. The Zero remained capable of the same tight turns, the same snap rolls, the same devastating low-speed maneuverability. But American fighters no longer accepted the invitation to dogfight. They dove from above, fired, and climbed away, using speed and altitude to control engagement geometry. The Zero pilots could turn inside any circle, but increasingly found themselves circling alone, watching their targets vanish into clouds or speed away at 380 miles per hour while their Seki 12 engine screamed at maximum power delivering 316. The engineering specifics reveal the precision of this trap. The mathematical reality proved inescapable. Turn radius equals velocity squared divided by the product of gravitational acceleration and load factor. At 180 miles per hour pulling for GS, the Zero turned a circle 500 feet across. At 350 miles per hour pulling for GS, that radius expanded to 1,900 feet. The P-40 at 350 miles per hour and for GS turned a 1,900-foot circle while maintaining full control authority. If the Zero slowed to tighten its turn, it entered a regime where American fighters could accelerate away before the Zero completed its circle. If the Zero tried to stay fast, its control forces increased beyond pilot capability. The equation permitted no solution that preserved the Zero's dominance. Japanese pilots understood their predicament but possessed limited options. Later war accounts describe Zero pilots attempting to force American fighters into slow-speed combat by feinting turns, hoping opponents would take the bait and decelerate into maneuvering fights. When that failed, as it increasingly did by 1944, Zero pilots resorted to desperate tactics, head-on passes accepting collision risk, shallow diving attacks hoping to catch climbing opponents, even ramming attacks as fuel and ammunition ran low. None restored the tactical advantage the Zero enjoyed in 1942 when Allied pilots did not understand that refusing combat sometimes represents the most effective tactic. The irony compounds when considering post-war aviation development. Modern air combat doctrine universally emphasizes maintaining energy, controlling engagement geometry, and exploiting specific performance advantages while avoiding opponent strengths. Fighters' design prioritizes speed, acceleration, and weapons range over turning performance. Air-to-air missiles engage at distances measured in miles, making dogfighting capability nearly irrelevant. The lessons American pilots learned fighting Zeros in 1942, maintain speed, control altitude, use boom and zoom tactics, became foundational doctrine that persists 8 decades later. The Zero forced American aviation to abandon WWI-era circling dogfights and develop approaches applicable to jet-age combat. The Mitsubishi A6M Zero achieved exactly what its designers intended, a carrier-based fighter with unprecedented range and maneuverability using minimal resources. It dominated Allied opposition for 2 years, inflicting disproportionate losses and forcing doctrinal revolution. But the design's fundamental compromises ensured that dominance proved temporary. Once opponents adapted to exploit the Zero's high-speed vulnerability, the aircraft's advantages became tactical traps, luring Japanese pilots into combat they could not win while American fighters dictated terms from regimes where Japanese designers' weight-saving measures translated into fatal weaknesses. The strategic implications extended beyond tactical aviation. The Zero's early dominance enabled Japanese operational objectives in the war's first 6 months. Carrier task forces struck Pearl Harbor, Darwin, and Ceylon with minimal losses, sinking battleships and destroying airfields because Zero fighters suppressed defending fighters and protected Japanese bombers. The Philippines, Malaya, Singapore, Java, and Burma fell to Japanese forces supported by air superiority that Zeros enabled. Had American fighters effectively countered Zeros from December 1941, Japanese operations might have faltered through unsustainable aircraft losses and failed objectives. But by late 1942, the operational balance shifted. American fighters using improved tactics neutralized the Zero's advantages, forcing Japanese forces to operate without reliable air superiority. The Guadalcanal campaign demonstrated consequences. Japanese forces attempting to resupply island garrisons faced American fighters that intercepted raids methodically, destroying bombers and forcing Zeros into defensive combat that negated their maneuverability advantage. The attrition proved unsustainable. Japan lost approximately 650 aircraft over Guadalcanal between August 1942 and February 1943, losses that training infrastructure could not replace with comparably skilled pilots. The broader lesson transcends specific aircraft or even aviation warfare. Systems optimized for specific performance parameters achieve dominance within that optimization envelope but create vulnerabilities outside it. The Zero optimized for range and maneuverability sacrificed armor, dive capability, and high-speed handling. Within its optimization envelope, long-range missions requiring sustained turning combat at 180 to 220 miles per hour, the Zero dominated. Outside that envelope, the design's compromises became fatal weaknesses. American fighters escaped the envelope by refusing to fight within it, forcing combat into regimes where American strengths mattered and Japanese advantages withered. Modern military systems face identical dynamics. Stealth aircraft optimize for radar invisibility at the cost of payload, speed, and maneuverability. Anti-stealth systems optimize for detecting low observable targets but remain vulnerable to electronic warfare. Every optimization creates specialization, and every specialization creates vulnerability to opponents who identify the optimization boundaries and operate outside them. The Zero taught this lesson 8 decades ago, demonstrating that victory comes not from optimizing specific parameters beyond all opponents, but from forcing opponents to fight in domains where optimization becomes liability. The personal dimension remains. Jiro Horikoshi designed an aircraft that achieved exactly what the Navy specified, using materials and manufacturing capabilities available in 1937 Japan. His solution proved brilliant within the constraints imposed. The Zero's early dominance validated the design philosophy and ensured production through war's end. Horikoshi never expressed regret for the Zero's vulnerabilities. Armor and self-sealing tanks would have made the aircraft too heavy to meet specifications. The Navy demanded specific performance, and the Zero delivered. That the design proved vulnerable to tactical adaptation and industrial attrition reflected strategic circumstances beyond engineering control. The American pilots who survived encounters with Zeros carried memories of an opponent that forced doctrinal revolution. Many expressed professional respect for the Zero's design and Japanese pilot skill, while remaining grateful for the industrial might and tactical innovation that eventually established American dominance. The fear that Zero encounters generated in December 1941 transformed into confidence by 1944, not through individual bravery but through systematic adaptation, better aircraft, improved tactics, superior training, and overwhelming numbers. The Zero excelled at fighting a specific kind of war, the war its opponents learned not to fight. If this story gave you a new way to see the Pacific War, like, share, and subscribe, and tell us which moment surprised you most. We'll return next week with another chapter in the war that changed the world.